The FHWA has an ongoing accelerated implementation and deployment of payment technologies program, which includes deployment of innovative technologies to improve payment performance and reduce agency risk. This presentation was prepared by Galen Baumgartner in November 2022 under the Development and Deployment of Innovative Asphalt Pavement Technologies Cooperative Agreement with the University of Nevada, Reno. Presenting today is Galen Baumgartner of Paragon Technical Services, Inc., Jackson, Mississippi. This material is disseminated under the sponsorship of the U.S. Department of Transportation in interest of the Information Exchange under the cooperative agreement listed. The U.S. government assumes no liability for the use of the information. The U.S. government does not endorse products or manufacturers. Trademarks or manufacturers' names appear in this material only because they are considered essential to the objective of the material. They are included for informational purposes only and are not intended to reflect a preference, approval, or endorsement of any product or entity. This presentation is arranged into 7 sections corresponding to the major headings of the companion Delta TC Binder Specification Parameter Technical Brief. First, Section 1 presents a brief introduction, followed by background information in Section 2. Section 3, Determination of Delta TC, discusses how Delta TC is calculated. In Section 4, elements impacting Delta TC are discussed. Section 5, Steps to Implementation of Delta TC, presents 6 systematic steps to aid in implementation of Delta TC as a specification parameter. Alternatives to Delta TC and ongoing research will be discussed in Section 6. Section 7, Status of Implementation of Delta TC, presents an overview of the status of implementation in the U.S. We will conclude with a summary in Section 8. We'll begin with a brief introduction. The objective of this presentation is to provide knowledge and technical support for responsible deployment of Delta TC as a specification parameter into asphalt binder acceptance specifications should state DOTs be considering implementation. The purpose is to provide some preliminary considerations, a yellow light so to speak, if a state DOT has pressing needs and wants to proceed with implementation while acknowledging that information on Delta TC continues to evolve. This project is sponsored by the Federal Highway Administration Project Deployment and Development of Innovative Asphalt Pavement Technologies, specifically related to deployment and technical support of the Delta TC binder specification parameter. An accompanying technical brief entitled Delta TC Binder Specification Parameter is available from the FHWA website. The difference in low temperature performance grade PG limiting temperatures, delta T critical, commonly referred to as delta TC, is an asphalt binder parameter that provides insight into relaxation properties of the asphalt binder that can contribute to non-load related cracking or other age-related embrittlement distresses. Delta TC is a calculated value using results, creep stiffness and creep rate, from the bending beam rheometer BBR test. It is intended to be calculated from data from asphalt binders that have been long-term age, rolling thin film oven range RTFO, plus pressure aging vessel PAV. Delta TC can also be on recovered asphalt binders from reclaimed asphalt pavement, RAP, and reclaimed asphalt shingles, RAS, or in combination of these with virgin asphalt binder. Delta TC may be used to evaluate any asphalt binder. Examples include neat asphalt binder with no additives, asphalt binder with additives such as polyphosphoric acid, PPA, and refined engine oil bottoms, or vacuum tower asphalt extender, RELB, VTAE, modified asphalt binders that has been blended with polymers or asphalt additives, and recovered asphalt binder containing RAP, RAS, or combination of these with virgin binders. Generally, Delta TC may be considered as an indicator of how effectively asphalt binders respond to aging or how effectively additives impact the response of asphalt binders to aging. Some state departments of transportation, DOTs, have implemented or intend to implement Delta TC as a part of existing acceptance specifications. At the national level, some research projects have considered and are considering delta TC as part of their studies. This presentation and the companion technical brief present a review and summary of current state of the knowledge of delta TC as a parameter to characterize asphalt binder behavior. Information presented is an excerpt and a summary from the Asphalt Institute AI State of the Knowledge Informational Series IS 240 available at the Asphalt Institute website, asphaltinstitute.org. The objective is to provide knowledge for responsible deployment of delta TC as an asphalt binder specification parameter should state DOTs be considering implementation. As information on delta TC evolves and the state DOT has a pressing need to implement, the intended purpose is to provide some preliminary consideration whether to proceed or not. The scope of this report is limited to the deployment of the delta TC parameter into asphalt binder acceptance specifications. An advantage of delta TC is it can be calculated in a straightforward manner from results of BBR tests already used in acceptance. Some brief background comments may provide information on the evolution of the delta TC parameter. The delta TC parameter was conceptualized during the Strategic Highway Research Program, SHARP, and later suggested as an indicator of pavement performance in a research project sponsored by the Airfield Asphalt Pavement Technology Program, AAPTP, Project 06-01, Techniques for Prevention and Remediation of Non-Load Distresses in Hot Mix Asphalt HMA Airport Pavements. The goal of the Project 0601 study was stated to identify simple asphalt binder and/or mixture tests which could predict imminent cracking or raveling so that pavement preservation strategies could be timed to delay or prevent damage of HMA pavements on general aviation airports. The study concluded that a new asphalt binder parameter referred to as delta TC had promise as a tool for neat asphalt binders that could be used to predict ductility and analyze durability related properties of aged asphalt pavements. Delta TC has evolved as a parameter that can be used to evaluate relaxation properties of asphalt binders. More information on the origin of delta TC can be attained from Chapter 2 of IS 240. Relaxation properties of asphalt binders expressed by delta TC values can affect several different types of asphalt pavement distresses, including non-load related cracking and other age-related embrittlement distresses. Only block cracking, as presented in this photo, has been directly correlated to delta TC. Several factors can contribute to other forms of distress: fatigue, edge, longitudinal, reflection, and transverse cracking, raveling, and potholes. It is most likely readily apparent the indirect relationship delta TC has with the pavement distresses listed in this table. While delta TC may be a contributing factor, additionally, pavement structure, environment, and loading are among factors that may also contribute to these distresses. How is delta TC determined? The delta TC parameter is an indicator of how effectively asphalt binder responds to aging and how incorporation of additives may impact the response of asphalt binder to aging. Delta TC is represented as the difference in critical load temperature values of asphalt binder according to the SuperPave performance grading methodology. Results from the BBR test ASTO T313 are used to calculate delta TC. The critical temperature, T sub C, for both creep stiffness, S, designated as T sub CS, and creep rate, M, designated as T sub CM, are determined at the specified performance grade PG limits according to ASTO M320, performance grade binder specification, or ASTO M332, MSCR performance grade binder specification. Conditions and limit values of 300 megapascals and 0.300 respectively. Delta TC is then calculated by subtracting the M critical T sub Cm temp from the S critical T sub CS temp. This figure presents a graphic depiction of delta TC. This is where the M value, the temperature where the M value is exactly M equals 0.300. This is where the S value exactly is equal to S equals 300 megapascals. The delta Tc is the differential between these two temperatures, or it's delta Tc equals T sub Cs minus T sub Cm, which gives us the delta Tc. In this case, the delta Tc is a positive 1.4 degrees Celsius. What does all of this mean? Depending on the values of T sub Cs and T sub Cm, the sign of delta Tc is either positive or negative, which indicates whether the binder's low temperature performance grade, Pg, is governed by its creep stiffness, S value, which is a positive delta Tc, or governed by its creep rate, M value, which is a negative delta Tc. A positive delta Tc value indicates that the binder is S controlled, failing the S criteria before the M criteria, while a negative delta Tc value indicates the binder is M controlled, failing the M criteria before the S criteria. The magnitude of the delta Tc value, or the absolute value, indicates the degree to which the binder is M controlled or S controlled. In this figure, you can see we have an unaged binder where we have M here and S here, and the delta Tc is a positive 1.4 degrees Celsius, which means that basically the S criteria fails before the M criteria. And here we have an aged 20 hours in a PAV, this same binder, and now you see that it's reversed. The S value is failing the M value before the S value, and now we have a negative 1.6 degrees separation for the delta Tc. And note the more negative values of delta Tc indicate more M-controlled asphalt binders, which are considered to have greater tendency to non-load related cracking. Again, this was zero aged and then aged at 20 hours in the PAV, and here we have a positive 1.4 degrees C, and on that 20-hour age we have a negative 1.6 degrees C. The negative delta Tc indicates that it is governed by the creep rate or M value, while the positive delta Tc indicates that it's governed by the S value or the stiffness of the binder. In this presentation, delta Tc values are presented as degrees Celsius. It is important to understand that the delta Tc value represents a difference in temperature, Celsius degrees, as opposed to a specific temperature. Additionally, the negative value does not represent a negative temperature, but that the parameter is M critical creep rate controlled. Again, the magnitude of delta Tc value indicates the degree to which the binder is M controlled or S controlled. The industry has pretty much accepted the degrees Celsius nomenclature, so we'll use this throughout the presentation. It's what will be used probably in the specification parameters. Research has indicated that more negative values of delta Tc appear to be strongly correlated to non-load related cracking and other distress related to poor relaxation properties. A delta Tc specification warning limit of minus 2.5 degrees C at 20 hours PAV aging and a failure limit of minus 5 degrees C at 20-hour PAV aging has been suggested for consideration as potential specification criteria. In other words, minus 5 is more negative than minus 2.5. Therefore, a delta Tc value of minus 5 degrees C is perceived to be worse than a delta Tc value of minus 2.5 degrees C. In this figure, if you recall, the non-aged binder, zero aging, had a delta Tc, positive delta Tc of 1.4 degrees C. And then after 20 hours of aging, we had a 1.6. Well, here we look at 40 hours of aging, and you see now it's a minus 4 degrees C, and versus 80 hours of aging, which we have a minus 7.3 degrees C. So you can see the effect of aging on the increase in the delta Tc. What are some elements that impact delta Tc? An asphalt binder's response to aging is the primary element affecting delta TC. As asphalt binder ages, the delta TC differential generally becomes greater and more negative, indicating what is believed to be loss of relaxation properties as the asphalt binder becomes more M value controlled. The effects of aging on delta TC parameter calls to question what degree of laboratory aging is necessary to adequately evaluate delta TC as it relates to field performance. There's not a simple answer to this question. Binders will need to be aged relative to the degree of distress with aging in the field. Let's try to summarize what we've discussed in a review of the data and the figures thus far. The first figure from the left to right is the original figure showing the positive delta TC of 1.4 degrees S controlled. After 20 hours of PAV, we have the negative delta TC of minus 1.6 degrees or M controlled. If the aging extended to 40 hours, the PAV aging we notice of the delta TC remains negative and has widened to minus 4 degrees. After 80 hours, the PAV aging of the delta TC extends to minus 7 delta TC. I would like to draw your attention to some important points. Often we are asked, why do polymer modified asphalts sometimes show issues with delta TC, but do not show issues with cracking? With this expanded figure, notice what happened to delta TC with aging. It went from positive to negative, S controlled to M controlled, or stiffness controlled to relaxation controlled, and we approached more negative values of delta TC. Notice that when we went from negative values of delta TC, where M equals 0.300, the stresses S of T of the material decrease. In this example, from the 20-hour PAV aging to the 40-hour PAV aging, stresses drop from about 4 megapascals to about 2 megapascals. This is about 2 megapascals here. Considering the 80 hours of PAV aging, we can see that the stresses are considerably less. What we see is the binder beginning to lose the strength it needs to resist cracking, as well as the ability to relax stresses. Simply put, with binders modified with polymers, the S value tends to be more constant with improved relaxation properties compared to non-modified binders or stiffer binders. From what has been presented, we can see that one of the more critical elements impacting the delta TC of asphalt binder is aging. Like extended aging of virgin asphalt binder, combining pre-aged materials such as RAP or RAS with a virgin asphalt binder could result in an asphalt binder with a more negative delta TC. Re-refined engine oil bottoms, REOB, vacuum tower asphalt extenders, VTAE, and other fluxing agents for softening and adjusting low temperature parameters of asphalt binders are also known to impact delta TC. As we just discussed, asphalt binders blended with polymer modifier can also be evaluated for delta TC. However, there are concerns on the validity of characterizing polymer modified asphalt binders using delta TC. Some features of elastomeric polymer modification may have a worsening effect on delta TC and therefore make it appear as if the polymer modified asphalt binders are exhibiting diminished durability. Combined effects of all these factors should also be considered. One element that we do not speak much of in the U.S. are air-rectified or air-blown binders. Air-rectified binders are somewhat pre-aged and would also affect the results of delta TC. This table shows that addition of recovered RAP binders to virgin PG 52-34 and PG 64-22 produce either decreasing positive values or more negative delta TC values with increasing RAP contents. The primary thing to note from this figure is that as the binders age, the positive delta TCs decrease or become negative or more M-controlled. For example, the PG 52-34 binder plus RAP B goes from an S-controlled delta TC of 2.2 to an M-controlled with more addition of RAP, the addition of more RAP. This gives a general idea of the impact of RAP on asphalt binders with respect to delta TC. You can see that most of these either have lessening positive numbers or wider negative numbers of delta TC. This was RAP in two different binders, three different RAPs, to give you the example of three different RAPs in two different binders. This table presents estimated delta TC data from RAS binders from the National Center for Asphalt Technology NCAT report 1601 as reported in TRB E-Circular 241 and additional data from the Asphalt Institute IS-240. RAS asphalt binder is highly oxidized and very stiff. Therefore, RAS is expected to impact delta TC to a higher degree than experienced with RAP asphalt binders. Calculation of delta TC of RAS asphalt binder is not as straightforward as with RAP asphalt binder due to RAS binder stiffness. This highlights some of the issues with delta TC. Extraction and recovery commingles the RAS and the virgin binder, whereas this does not occur at the same extent in the field. You can notice that these numbers for delta TC are quite wide for the RAS binders, and the reason for this is you notice that the T sub C temperature is much higher than we would see on an asphalt binder used in paving. These numbers are typically in the negatives for asphalt paving binders for both the T sub C high and the T sub C low. Some steps to implementation of delta TC. One of the more important steps to implementation of delta TC is familiarization. Familiarize yourself with delta TC. Understand it. Don't just look at the number. Understand, as we have discussed, what happens to stiffness of the binder with respect to aging. What happens to M value with respect to S value? How does it affect the performance of the binder? Asphalt Institute IS-240 is a great starting point to really familiarize yourself with delta TC. This is about 70 pages of valuable information. Note that the delta TC parameter is primarily intended to address durability related to stresses. Understand that more negative values may have an indirect impact on other forms of cracking other than block cracking. However, block cracking is the only mode of cracking that has been directly related. If you have a cracking issue, clearly understand the performance challenge to be addressed. Ensure that delta TC is the proper parameter to address the issue to be addressed. Understanding of a problem first may make the solution more attainable. The delta TC parameter is more than a number. It is not a panacea to cure all cracking issues. Just specifying a number will not address all cracking issues. We really need to understand what is occurring with the pavement performance and with the binders. Laboratory evaluation of existing pavements may be necessary. Realistically, they will be necessary if we truly understand the issue. There are alternatives to delta TC parameter, and some of these may be more appropriate. Currently, there does not appear to be strong industry consensus as to the effectiveness of delta TC as a specification parameter. Overall sentiment of agency practitioners and others in the asphalt pavement technical community is somewhat mixed. Asphalt Institute IS-240 suggests a systematic approach for consideration and implementation of delta TC. This framework entails 5 steps. Step 1, clearly identify the problem delta TC is intended to address. Step 2, determine whether delta TC is the most favorable alternative. Step 3, select an aging method to ensure delta TC measurements are representative. Step 4, evaluate existing pavements that exhibit diverse cracking behavior. And step 5, evaluate delta TC results obtained to determine simulative aging protocol. A complementary element to the recommended framework is a concerted effort with all entities working together regionally to facilitate uniform transition for the asphalt industry. Alternatives to the delta TC parameter. Cracking has become the predominant distress affecting pavement performance in the United States. Over the past several years, numerous new asphalt binder cracking properties have been evaluated. Delta TC is just one such property considered. Correlations between delta TC and other radiological parameters have been suggested, such as the Glover-Roe parameter. Relationships of other rheological parameters have also been discussed, such as the rheological index, R, as a parameter describing the shape of the rheological master curve, which is critically related to the shape of the relaxation spectra and the ability of the material to relax stresses. Additional master curve related parameters have been suggested, including crossover temperature, T sub VET, and crossover modulus, G star sub C. Asphalt technologists have also suggested specifications limiting S at the critical M value. For example, specification limits for acceptable delta TC values, or specification of a minimum S value where the M value meets a current specification limit of 0.300. Establishing a minimum S value acceptance criteria is a reasonable alternative and does a reasonable job of screening asphalt binders with large negative delta TC, as well as limiting the effects of improper use of deleterious additives. More recently, ongoing research indicates that the delta TC parameter may be more effective at identifying effects of deleterious additives in asphalt binders than as a predictor of asphalt binder cracking and durability. Like the minimum S suggestion, this research prefers a minimum S value for a given M value, except for incorporation of modeling concepts to suggest variable S value minimums applied to variable M values for specific values of delta TC. This may sound complicated, however, it's quite simple. For example, if delta TC is minus 8 degrees C, then the specification limit would be a minimum S value of 125 megapascal with an allowable increase of the minimum S value to 150 megapascal for M values greater than 0.32. Considering these observations of the delta TC parameter's functionality to identify deleterious additives, it is understandable that the delta TC parameter could be used to identify presence of non-bituminous asphalt binder components. However, more straightforward methods of restricting use of unwanted asphalt binder additives are possible. Recent work by the Western Research Institute, WRI, under NCHRP Project 9-60 builds on previous research to address durability and cracking issues related to asphalt binders. A delta TF parameter was proposed by the Project 9-60 researchers as the asphalt binder property relating most closely to durability. The delta TF parameter incorporates a binder fracture test using asphalt binder cracking device ABCD. This uses results from delta TC and delta TF after 20 hours of PAV aging. Delta TC uses the standard BBR results to calculate delta C sub S and delta T sub M equal than delta TC. The delta TC threshold is set at -2 for warning and -6 for failure. If delta TC fails these limits, then delta TF is employed, where delta TF is equal to ABCD T sub CF minus BBR T sub CS, or delta TF equals the ABCD T sub CF T critical F minus BBR T critical S, or T critical S. Status of implementation of delta TC. A recent state-by-state review of Asphalt Institute U.S. Binder Specification Database of published asphalt binder specification revealed 10 state DOTs have adopted a delta TC specification parameter. This is slightly different to what the state DOTs reported by AI IS 240 to have adopted a delta TC specification parameter. Texas originally specified a delta TC of -6.0, but have since removed this requirement and are evaluating other methods and considering the relationship of S value to a given M value. Most but not all these state DOCs adopted minimum limits of delta TC of -5.0. Oklahoma specifies delta TC of -6.0, and Utah requires delta TC of -2.0. For the most part, the split between state DOTs using 20-hour and 40-hour PAV aging protocols show that the states in warmer climates using PG64 binders tend toward 20-hour PAV aging, while states in colder climates using PG58 binders prefer 40-hour PAV aging. In preparation for this webinar, a quick check of state DOT specifications did not indicate changes in this status. The 10 states in green are the states that have Delta TC specifications. Delaware, 40-hour PAV minus 5.0. Florida, 20-hour PAV minus 5.0. Kansas, 40-hour PAV minus 5.0. Maryland, 40-hour PAV minus 5.0. New Jersey, 40-hour PAV minus 5.0. New York, 40-hour PAV minus 5.0. Oklahoma, 20-hour PAV minus 6.0. Pennsylvania, 40-hour PAV minus 5.0. Utah, 20-hour PAV minus 2.0. Vermont, 40-hour PAV minus 5.0. Some of these states, I mean, we've got to realize that's what we've been through in the past 2 years. So some of this information may not be correct. It's kind of hard to find it. I think once we get back things going back to normal, that we'll be able to verify these numbers. But this is what we got when we did the survey back in 2020. As well as what's been gotten from the published specifications. Some summarizing comments. This presentation and companion technical brief present a review and summary of the current state of the knowledge of delta TC as a parameter to characterize asphalt binder behavior. It relies on a state of the knowledge document by the Asphalt Institute entitled Use of the Delta TC Parameter to Characterize Asphalt Binder Behavior. The objective of this presentation is to provide knowledge and technical support for responsible deployment of Delta TC as a specification parameter into asphalt binder acceptance specifications should state DOTs be considering implementation. The purpose is to provide some preliminary considerations, a yellow light so to speak, if a state DOT has pressing needs and wants to proceed with implementation while acknowledging that the information on Delta TC continues to evolve. A brief description of Delta TC, how it is determined, and its relevance in characterizing the behavior of asphalt binders has been presented. Elements influencing the Delta TC parameter were discussed. Of significant issue is the degree of laboratory aging to be useful and practical for specification purposes. Discussed were possible steps to implementation of the Delta TC parameter. Also discussed were alternatives to implementation of the Delta TC parameter. A brief overview of the current state of implementation of the Delta TC parameter in the U.S. was presented. This concludes the presentation of the Delta TC binder specification parameter. Questions and comments are welcome at this time. Thank you.